I want to thank, of course, all of the friends at IFAE, the Institute for Physics of High Energy here in Barcelona, and of course, la Fundación La Caixa for the hospitality. And it's my pleasure to entertain you for the next hour or so with the topic of the search for dark matter at the Large Hadron Collider at the LHC. Now, you don't have to be an astronomer to be blown away by the beauty of images like this. This is a cluster of galaxies. There are thousands of remote galaxies shown here. You can start counting them, and you will never get to the end of it. On the other hand, however beautiful this image is, some of the most exciting aspects of this image we cannot really see. They're not evident. They don't show up. Unless we do something more sophisticated and we look at it with different eyes. There is a phenomenon which is known since the days Einstein discovered general relativity, and that is in fact 100 years ago. Gravitational lensing is a phenomenon that those of you who attended the first lecture by Gary Bernstein have already learned about. And the idea is that mass can curve light in the same way that a lens would do. The lens curves light if light goes across the lens, across the crystal, while gravity acts at a distance. And if we have a beam of light going next to the sun, for example, it will be slightly tilted. So if we have a cluster of galaxies, like shown in the middle of this slide, we are sitting on the Earth, in the bottom, and far away from the cluster of galaxies, there are other galaxies. As their light comes towards us, we will see it being deflected. So that will create images like the ones that we would see with light going through a glass. And since the system of galaxies, the cluster of galaxies, I don't have it, is not perfect, we will see distortions, pretty much like the phenomenon of aberration, of not having proper lenses. So if we look more closely at some of these galaxy clusters, we see phenomena like those depicted in this picture. You see those stretched bands of lights. What they are, they're not imperfections of a telescope. It's just the length image of a galaxy sitting in the far background. Of course, the more mass there is in the galaxy cluster, the more the light will be bent. It's like saying if we have a very thin lens, it will not do much. If we have a very thick lens, it will corrupt the trajectory of a light much more. So by quantitatively analyzing the way the image of these galaxies gets distorted, we can extract how much mass there ought to be in this cluster of galaxies. And what we learn is that there is much more mass than what we actually see. Because we see those galaxies, we see that light, we can estimate how much there is because we know more or less a given galaxy with a given light, how many stars there should be in it, and that's not enough. So there has to be something else, and this is something else, is what we call invisible dark matter. This is just one of the many manifestations in the cosmos of dark matter. It's one of the most recent ones. There has been, as was reviewed in the previous lecture by Bernstein, there is almost 80 years knowledge about the existence of dark matter, but it's observations like these that really put on a very firm ground its existence. We're dealing with something which is invisible, and we claim that somehow we see it because we found a way to see dark matter, which, being called dark, we don't see. So there seems to be this inconsistency in terminology. How can we be aware of something that we cannot see? Of course, this is a relatively common phenomenon. This is a picture from Salvador Dalí. It's called surrealist composition with invisible figures. Indeed, there are no bodies here, but we see their shape. So we learn that there has to be something just because we see a trace imprinted on the bed and on this armchair. So when we say that something is invisible, we're already making a statement about something being there. Proving the existence of the invisible is, in other words, providing evidence that there is something where there appears to be nothing, and turning the invisible into visible is one of the main drivers of scientific progress. It's a very general phenomenon in science. It's a very basic process, and it's something that takes us from the realm of magic and superstition to the domain of science. Think of the plague, for example. We now know what its origin is, it's bacteria, but at the time, you know, the most incredible reasons were found. Many people were burned because they were thought to be carrying plague. So that's what I mean by moving from superstition to science. Now, this is another picture, again, by Dalí, who was a bit obsessed with this idea of the relation between visible and invisible. It's called the invisible harp. Now, it's not obvious that there is something invisible here because we do see objects. Even less obvious is that it's actually a harp. So the next step is establishing the nature of the invisible. And the goal of modern physics is precisely to unveil the invisible, to point out that there is something there, but to give it substance, to find what it is, and to explore its consequences on the universe. So understanding the origin of dark matter is indeed one of the most puzzling and exciting and challenging problems in science today. Now, why is it a problem? Because I just told you that there has to be much more mass than we see in the forms of galaxies and stars. And of course, you know, there are many things that we don't see because they're not visible. If we turn off the light at night, we don't see anything. And it doesn't mean that there are invisible objects, it's just that we don't see them, but it's objects that we are surrounded of. So how do we know that this missing mass, this missing matter is not very simply some obscure lumps of ordinary matter, such as dust, rocks, comets, planets, maybe some funny molecules, some funny forms of chemistry that aggregates objects in different ways? So it all boils down to what we actually know about ordinary matter. It's by knowing deeply the behavior of ordinary matter that hopefully we can conclude something about whether what we now call dark matter is indeed a new extraordinary phenomenon or it's something very trivial. So I will now spend a few minutes telling you about what we really know about ordinary matter. And what we know about matter is encoded in the so-called standard model of particle physics. That is the theory that explains matter as we know it in terms of fundamental constituents and fundamental interactions. Matter is made of molecules. Molecules are made of atoms. Inside atoms, there is a nucleus surrounded by electrons, and this is basic chemistry that's being taught in schools for many, many decades now. And in the core of the atom, in the nucleus, there are protons and neutrons. And what is now known since at least 60 years is that proton and neutron themselves contain their own little universe. They're not point-like elementary objects, but they're made out of quarks. And there are 3 quarks composing both the proton and the neutron. And there is a very limited number of quarks that are enough to explain everything we see. In fact, what we see and surround us here is really made just out of 2 quarks, the so-called up and down quarks, out of which we build proton and neutrons. And then there is the electron, that goes around, and of course, well, not of course, but there is a neutrino, a partner of the electron, which is a particle that, as we will see, shows up in radioactive processes. Now, this structure of these four particles are known, for all we know, are absolutely point-like. They don't have any structure. There is no indication of there being something inside the electron or inside the up and down quarks. And this structure is repeated 3 times with other quarks and other partners of the electrons. These we call leptons, the electron, the muon, and the tau, who share all of the features of this first family. They're simply heavier. And by being heavier, they live for a very short amount of time because they immediately decay to the lighter objects. All of these elementary particles are held together by interactions in a way which is very simply described by very basic building blocks. These building blocks are the idea that, for example, in the case of leptons, so the electron, it interacts with a photon. The photon is light. It also happens to be the carrier of the electromagnetic interactions. The electric force that generates when you have charges or when you have some magnet, it's transferred by the exchange of photons. Radioactivity is mediated by 2 other particles, the W and the Z boson. And this is all that the leptons are subject to, plus, of course, gravity. So these very basic building blocks, in a way very similar to the one of the Lego sets, the Lego blocks that kids play with, in which you have a finite number of objects and a finite number of ways in which you can assemble them. But out of these limited and simple rules and objects, you can build something arbitrarily complicated. So out of these basic 3 particle interactions, you see we can build an interaction between 4 particles, because the photon that's been exchanged by these 2 electrons, of course, can interact with another electron. And this is the basic building block of the electromagnetic interaction between charged particles, between electrons. So it's very simple. Of course, for each of those little drawings, there is a very complicated mathematics. There are equations behind that quantify precisely what is happening. In the case of quarks, again, the constituents of the protons and the neutrons, there are interactions with the photon because they are charged, electrically charged, so they're subject to electromagnetism. They are subject to the weak interactions, which are responsible for radioactivity. After all of the radioactive phenomena that we hear about are related to, for example, uranium decaying, all of the leftovers of a nuclear processing taking place in nuclear plants. They come from transitions between protons and neutrons mediated by these particles. And in addition, relative to the lepton, they also interact with the gluon, which is, as the word says, glue. It's what binds them together inside the proton and the neutron, 3 quarks bound together by the exchange of gluons. So it's a very basic and simple phenomenon. We can construct more complicated things and describe, for example, radioactivity. Radioactivity is a process by which a nucleus with a charge Z decays to another nucleus with a different charge emitting an electron and a neutrino. When these phenomena were first discovered, it was assumed to be a transition between neutrons decaying to a proton, an electron, a neutrino. With a standard model, we know that inside the proton and the neutron there are these quarks, and therefore we describe a process in terms of transitions between quarks at a more fundamental level. So again, not only we can build complex objects out of these simple building blocks, but we can also describe the interactions among complex objects by using these very basic and fundamental sub-processes. Now, a drawing like this, a process like the one you see here, may look very abstract to you, but if we are here, it's really thanks to something like this phenomenon, because a process like the one I just showed is really the basis for the generation of energy inside the stars. It's conversions between protons and neutrons with emissions of electrons, neutrinos, which are energetically convenient. They transform the energy of gravity that pushes the sun to squeeze, because of course the sun is attracted by its own gravitational field, like we are attracted to the Earth, and it gets pushed, the pressure goes up, the temperature goes up, and that energy is transformed into a seed for nuclear reactions that are what ultimately gives rise to the energy emitted by the sun and received on Earth. When all of the fuel for these reactions is consumed within the sun, or in general within a star, then the star is subject once again to the gravitational force that will squeeze it. And if the star is sufficiently heavy, this process, this implosion, is really dramatic, very fast, and a lot of gravitational energy is transformed, again, helps producing more nuclear reactions that then lead to the creation of heavier elements like silicon, iron, gold, uranium. At the end of this, there will be a gigantic explosion. That's what leads to phenomena like these giant stars, red giants or supernovae exploding occasionally in the sky and seen by telescopes. And all of the residues of these nuclear processes, silicon, iron, gold, uranium, they disperse in space until they hit some cloud of, say, hydrogen that's undergoing its own initial process towards the formation of a new solar system. And they will contribute, they will aggregate with the hydrogen, with the matter that's already there. Eventually, they will form planets, planets like the Earth, in which we do find silicon, iron, gold, uranium, and all of these heavy elements. So all of this is understood. We understood where the uranium, the gold, the silver that we find on Earth come from, what's their origin. Okay? It's not just that, but all of the nuclear, chemical, electrical phenomena, everything that we literally see around ourselves, the atomic structure of the elements, the properties of metals, their conductivity, semiconductors, everything that is crucial for the functioning of your cell phones or computers, for example, is understood of a basis of electromagnetism, quantum mechanics, and those basic forces I described earlier. And this description is not just qualitative. I gave you the qualitative picture, but it's actually quantitative because there are equations behind all of this, so we can really calculate and estimate what the various processes are. And this pertains to all of the phenomena that we see around ourselves and what we measure in the laboratory. Now, dark matter, we cannot measure in the laboratory, not yet, and we don't see it because it's dark. So even though it's something that may not be understood, it's not in conflict with my statement here. Now, we understand so much that we can be so bold as to extrapolate back in time the way the universe was. We know that the universe is expanding, and we can just extrapolate back to the way the universe was long ago, when everything was much more compressed to a point in which everything was really, there was no free space between galaxies, there were no galaxies, there was no free space between planets and stars. Everything was like a very dense and hot gas. And this understanding can go down all the way to something of the order of 10 to the minus 10 seconds after the Big Bang. So 1/10 of a billionth of a second, because at that time, the temperatures and therefore the energies of the particles moving around were comparable to the energies that we can explore today in our laboratories, like at CERN. So the physics that took place after 10 to the minus 10 seconds is something that's been tested and known, and that we can rely upon to extrapolate back. In particular, that's good enough to take us across this period between a second and 3 minutes, in which all of the light elements that we see in the universe, the hydrogen, of course, helium, lithium, these elements were created. And we can calculate, so this is a picture, and we go back to the question of how do we know that dark matter is not an obscure lump of ordinary matter. This picture shows as a function of temperature, and therefore as a function of time after the Big Bang in seconds, gives us the fraction of the composition of the universe in terms of protons, neutrons, helium, deuterium, helium-3, tritium, beryllium, lithium, etc. So we can calculate on the basis of the equations of the standard model that we tested and we know to work, we can calculate as the system cools down in the course of the Big Bang, how much is left of, is created of all of these elements. You see, they weren't there at the beginning. At the beginning was just protons and neutrons, and as the system cools down, protons and neutrons get together, stick together, and through nuclear reactions give rise, start building up heavier and heavier systems. Now, it turns out that the precise fraction of how much deuterium, helium, lithium is left over at the end of this process depends on the amount of ordinary matter, the amount of matter that's built out of the basic objects of the standard models, that's built out of protons, neutrons, and electrons. And this is what comes out. The input is the measurement of how much lithium, helium, deuterium, and helium-4 there is. You see that if we were to choose a different amount of ordinary matter, for example, here, we would not be matching, then we would have a line going up, and we would find less helium than we have, more deuterium than we have, more helium, and a different amount of lithium. So this is the place where, in fact, all of the observations today match, and it corresponds to an amount of ordinary matter that indeed is much less than what is required to explain the phenomena related to dark matter I was explaining before. So the amount of ordinary matter present in the universe is precisely determined by the astrophysical observation of the relative abundance of light nuclei, and this amount is completely insufficient to account for the quantity of dark matter. And that is why we can claim with certainty that dark matter is not just a lump of molecules or some planet or some dark star that's burned off everything, but it has to be a completely new entity, a new object. And the amount of it is actually staggering. It's not like a minor fraction. As I said, a lot more dark matter than visible matter has to be there to explain the observations. And in fact, if we make a pie of the amount of energy in the universe, well, a large fraction is what is called dark energy. Dark energy, I will say nothing about. It's not particles, it's something else. And it's something to which a whole conference, in fact, I believe it's the next one, will be devoted to a conference by Dr. Eisenstein. So dark matter is 23% of the energy of the universe. And we have about 5% of ordinary matter, of which a small fraction, 0.5%, is indeed luminous. This is stars, gas that we can see. There is indeed a part which is not luminous, so it's also dark, but it is ordinary because it's accounted for by the discussion in the previous slide. So this is indeed planets, dead stars, or dust. But this is only 4%. So we still have this 23% to account for. So dark matter studies focus on four directions today. On one side, we want to do more of these studies on a cosmological scale, in which we look at observations of galaxies, for example, lensing. Now there are a lot of studies on galaxy cluster collisions, for example. So all of these phenomena that help us learn something more about dark matter in this very, very indirect way, namely through gravitational lensing. And that's something that Bernstein described in his first lecture. The other direction is what's called direct detection, which means since we are surrounded by dark matter, there ought to be dark matter flying around even as we speak. And indeed, there is. So is there any way we can intercept this dark matter? And if this dark matter has specific properties, then in principle, yes, it can hit nuclei of very sensitive detectors based on, say, silicon technology, for example. And by hitting a nucleus in the crystal, the nucleus will recoil, will deposit a signal that can be captured by the electronics and can be reported as the observation of the diffusion of a dark matter particle. Now, this will be described by Bertone in the fourth lecture. Dark matter tends to cluster in the center of galaxies, and if dark matter interacts somehow, it can annihilate with itself and give rise to radiation. It's not necessary, it's not necessarily true that it has to happen, but it could happen, and therefore it's important to look for this phenomenon. This is called indirect detection, namely satellites now, so experiments in orbit around the Earth sensitive to radiation, say gamma rays, for example, X-rays, detect radiation which is unaccounted for by normal astrophysical phenomena and with characteristic features that could indicate the annihilation of dark matter. This again will be covered by Bertone. And finally, the fourth direction is to directly produce dark matter. All of these three first bullets relied on using the dark matter that's around, that was created at the beginning of the Big Bang. So it's a relatively passive attitude. In this fourth bullet, we want to be active. We want to create dark matter in the lab. And once we have it, we can study it much more easily, of course, than if we can only have indirect access to it. Now, none of the particles described by the Standard Model, as I said, has the properties to account for the dark matter observed in the universe. So one could argue, well, you know, the Standard Model is wrong because it doesn't describe dark matter. I have to start from scratch, building up a completely new theory. Well, that's, you know, people have tried. It just doesn't work because the Standard Model describes so many things and so beautifully that you just cannot give it up. There is absolutely no substitute for that. So if indeed the Standard Model can explain everything except dark matter in our universe, it's reasonable to expect that to understand dark matter, it's enough to just extend a bit, to add something to the Standard Model. Could be additional particles and some interactions, but overall, we keep the conceptual framework of particle physics and of the Standard Model. So what we are after is you know, this extra particle that is floating around and is dark matter. That is the simplest possible explanation and directions for research. If we look at the properties of dark matter in the sky, we do get some constraint. You cannot come up with an arbitrary model of dark matter. There are very strong constraints. Nevertheless, there is still the possibility of proposing different scenarios. One scenario for dark matter is that it is heavy neutrinos, so a particle like the neutrino, but heavier than those we know, for example, or axions, which is a particle I will not be discussing. It's very, very, very light, very, very weakly interacting. It's completely idle in a sense, and its role is just to be there and play dark matter. We cannot possibly produce it, and it wouldn't interact with our detectors. And then WIMPs, which is the acronym for weakly interacting massive particles. So it's heavy particles that interact weakly with the Standard Model matter. And there are many theories beyond the Standard Model that have precisely objects in them with the features and properties of WIMP particles. What's more interesting is that by adding the constraints that come from the observation of dark matter, the cosmological observation, we find that WIMPs have masses and interactions. In order for them to be dark matter, they must have masses and interactions that could allow their both direct and indirect detection, as well as the creation in the modern accelerators. So the question is, how do we test these theories, and in particular, how can we create dark matter particles if we wanted to? And the key point when you want to create something new, a new particle, is the very famous Einstein's equations, E equals to mc squared, that says that once you have a mass, you can convert that mass into energy. But the way we use it is just turn a bit around. So we do a simple algebraic operation. We take c squared underneath, and now we read it from the right to the left, saying that mass is equal to energy divided by c squared. In other words, if I have an amount of energy, I can use it and convert it into mass. And this is what we do. We take particles, possibly of small mass, but of great energy. We accelerate them to large energy, and we have them collide so that we can focus in a small points a large amount of energy. And out of this energy, we can then create an amount of mass, a particle of mass m, which is given by this relation. So we can get a lot of energy out of a particle by accelerating it. And there is a very precise relation between the energy of a particle and its velocity. And the relation is given by this equation, where c is the speed of light, which is, as you know, a fixed number, and it's the largest velocity that any object can have in the universe, and v is the velocity of the object. So if you know a bit of algebra, you will see that when the velocity becomes of the order of the velocity of light, v over c becomes of order 1, because they're equal. 1 minus 1 becomes a very small number, and if we have a very small number in the denominator of this relation, this whole thing becomes very, very large. And it's obvious. You accelerate, you bring to very high velocity a particle, and its energy goes up. What is less obvious is that its energy would become infinite if the velocity were equal to the velocity of light. We don't have to push a particle to infinite velocity to get infinite energy out of it. And here is where the LHC, which is the Large Hadron Collider, enters. This is a tool precisely to accelerate protons, in particular, to very high energy, and use them for the search of new particles, to get enough energy to create large masses. So the LHC is a tunnel of 27 kilometers built in Geneva. This is the airport, so that's the runway. It gives you an idea of the extent of this object. You see smaller circles here, and that's because, as in your car, you cannot start right away at 150 kilometers an hour. You have to go through different steps. You have first gear, second gear, you have to accelerate. It takes a bit of time to build up velocity, and this is what happens at the LHC. There is, at the beginning, we just produce the proton. At the beginning is at rest. We give it a bit of an acceleration in a linear collider. It goes into a first circular collider, which is only 150 meters in circumference, and then a bigger one, 600 meters, and then a bigger one again, 7 kilometers, more recent, and then finally it gets injected into the LHC, which is, as I said, a 27-kilometer tunnel, and everything is located between 100 and 200 meters underground, of course, in order not to interfere with life on the surface, highways and people living, etc. So protons have to be guided on this trajectory, so it requires magnetic fields. A charged particle moving is bent by a magnetic field. So we're accelerating protons in opposite directions. We need magnetic fields pointing in different directions, and that means that we need two separate rings to store the protons. So this is the field that's created in which there are magnets with opposite polarity pointing up and down, which are distributed all around the ring and allow the protons to go around. So these objects are the most amazing thing you can imagine of in terms of technology. They have a field which is almost 150,000 times stronger than the magnetic field of the Earth. So you want to make sure you don't get close to it. Otherwise, your watch would be rip away your hand. It's built out of superconducting niobium titanium cable. It's superconducting, so it operates at a temperature which is close to the absolute zero, 271 degrees below freezing temperature. And it's bearing, it's embedded in superfluid liquid helium. Each of these objects, which are 15 meters long, weighs 35 tons. And they're slightly bent because they have to go in a circle. So all of these magnetic forces are such that when they touch each other, the pressure that we have to keep it in shape, as opposed to go straight, is a pressure of the order of 1,500 kilograms per square centimeter. So it's really very powerful objects. And there is 1,232 of them distributed around to keep the protons. The energy of a beam is 7,000 giga electron volts. That giga means a billion, so it's 7,000 billions, so 7 10 to the 12 electron volts. Now, the electron volt is the energy that you gain if you go across a field of 1 volt. The batteries we use at home are typically 1.5 volts, so that means that we need 5 trillions 1.5 volt batteries if we want to replicate the energy that is necessary. Of course, in the LHC, we obtain that energy in much smarter ways. Because if you really wanted to use 1.5 volt batteries, looking at the number, and you put them one next to the other, you would have about 100 million kilometers, which is the distance between the Earth and the Sun. So if you were naive to build an accelerator like that, you would need to fill up batteries between here and the Sun, which is obviously not a very effective way of doing it. At this energy, the proton goes so fast, you remember the equation between the energy and the velocity. So with this, in order to achieve this energy, the proton has to move at a speed which is close to the speed of light by 1 part in 10 to the minus 8. So it's 0.9999999 times the speed of light. That means that a proton at that speed, if we shoot it towards one of the closest stars, say Alpha Centauri, and we shoot at the same time a beam of light, the proton will get to Alpha Centauri about a second later than the light. So it's traveling so close to the speed of light that even such an interstellar travel would get the proton there almost on time. So it's really unbelievable. Altogether, when it operates, there is a large number of protons inside the ring, 10 to the 14, so a million billions almost. But at the end, the proton is so light that this is 10 to the minus 10 grams, so absolutely nothing. Nevertheless, this very tiny amount of matter has so much energy that what we get stored in the beam is 350 megajoules, which corresponds to the energy released by 80 kilograms of TNT. It's a train going at full speed. So you take the energy of a train traveling at full speed, and you put it into an amount of matter which is only a tiny fraction of the weight of a mosquito, 10 to the minus 10 grams. And once that's in place, protons go one way, other protons go the other way, and they collide inside experiments like it shown here. And out of a collision, that's where all of this energy is concentrated and operated. So there are big detectors. This is a man sitting next to one of these big detectors. This is the Atlas detector, which is the detector to which the local IFAE group gave very important contributions to the construction of and to the analysis of data. So this is part of the Spanish pride at CERN. This is a picture while the detector was being built. Again, here there are people. You see what's the scale of the whole enterprise. And it's a huge thing to look at something which is extremely small. And what comes out of this collision is a lot of fragments, a lot of particles. And we try to, so here the scale is of the order of few meters. That's the scale of a detector. And if we want to go and focus inside, we have to go very, 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 very close to the interaction before we understand and we see the fundamental processes taking place. In fact, we have to reduce down to the size of 10 to the minus 13 or 14 centimeters, which means a million billion orders of magnitudes zooming in if we want to see what precisely happens. So we can extrapolate from this picture down with a scale factor of the order of a million billion times to rephrase what's seen by the detector in terms of, once again, our friends, namely these very basic free particle interactions. This is a pictorial example of what happens when two protons, you see the protons here with free quarks, the other proton with free quarks. As they approach each other, they start radiating, and the individual objects that come out of it can interact with the objects that were sitting inside the opposite proton, and various phenomena can take place. And by reconstructing what the structure of a final state, and each event, of course, will give rise to slightly different phenomena. So we will have big catalogs of different configurations in the final state. There are several million events produced each second. About thousands of them are recorded by the experiment and are studied later on to look at the details. So the mapping between what is seen and what we assume on the basis of a standard model is happening is what allows us to learn about what has happened. And possible deviations from what we expect are indications of new phenomena taking place. So this is one example of what comes out. This is, I'm sure that all of you who are here are interested in science. You must have read about the news of the discovery of the Higgs boson. The Higgs boson, once produced, can decay in several ways, one of them being Higgs going to two Z bosons, and each Z boson decays to a pair of positron and electron. So the final state is this 4-electron object. And this is a snapshot of one event collected by the ATLAS experiment in which 4 particles among, you see, the hundreds that are produced are identified as being electrons. What is special about this event that makes it a possible Higgs candidate is that the total energy of remember the relation between the mass and the energy. If I have a particle with a given mass that decays to other particles, the sum of the energies of the particles it decays to must be equal to the mass of the original particle. That is energy conservation. So the signal for a new particle being produced is that the sum of the energies of the decay products is always the same. And this is indeed what we observe. We observe that on top of a noise background, namely other processes, there is a coherent build-up of events. These are number of events detected as a function of the total energy of the 4 electrons. And you see that there is this sharp peak. There is a peak here as well, but this is not a new discovery. That corresponds to a Z boson, a particle that was already known. So it's good that this is seen. It's a confirmation that everything works properly. But the big discovery is this peak here that corresponds to the creation of the Higgs boson. So again, the process is we start from the data, we look at them, we identify quantities which are of interest, we plot them. In this case, we have this peak resonance, as we call it, as an indication of a new particle. And from there, we go back and we reconstruct the underlying process. And in the case of a Higgs boson, once again, we can, out of these simple free particle interactions, reconstruct the whole thing that led to the creation of a Higgs boson via gluons emitted from the initial protons, its decay to Z's, and their decays to electron pairs. In the case of dark matter, we would be doing exactly the same. We speculate the existence of new interactions and new particles with the same principle. These are some examples that emerge in possible various theories beyond the Standard Model aimed at explaining dark matter. But here the dark matter, which is this chi 0, I say chi because we call it chi. Here it looks like a x, but it's actually a chi, the chi Greek letter, so I will say chi. Interacts with a quark, and with this quark with a tilde, which we call squark, quark with the S in front, because this comes out in theories like supersymmetry. So the S of supersymmetry is inherited by the particle. So we have this vertex. We have another vertex in which there is the W boson of the weak interactions interacting with the chi 0 and the chi plus. This is a partner of the chi 0. Or we can also have the Higgs decaying to these dark matter particles. So all of these interactions are not in the Standard Model, but in principle they could be there if we had the dark matter particle in these models. And out of these we can build aggregate interactions. We take two of these, one on the upper side, one on the lower side, and you see we mediate the interaction between quarks, for example, and dark matter, or between dark matter and W bosons. So depending on how we look at those diagrams, you remember there were two quarks, so Standard Model objects, and there were two dark matter objects. And we can use the Standard Model objects to produce a pair of dark matter. This is what we would be doing at the LHC. Or we can take a dark matter particle, have it interact with a Standard Model particle, like the proton, and then recoil, and then scatter away. And this is what the direct detection experiments would do. Or we could take two dark matter particles here and annihilate into two Standard Model particles. And this is what the indirect search for dark matter would observe, because these Standard Model particles would decay eventually to radiation. So starting from the same underlying theory, and here is a question mark in the initial blob because we don't know exactly what it is, that's what we want to find out, but assuming that there is something that mediates these interactions between dark matter and the Standard Model particles, we would have access to these three possible probes of dark matter. And again, these will be discussed by the direct and indirect will be discussed by Bertone next time. So at the LHC, typical processes are these. I have a quark, I have a gluon. From the two protons, they interact and they create a squark and a dark matter particle. And then the squark itself is heavy and would decay, still using the same diagram, into a quark and a dark matter particle. Something similar can be built by producing the squarks in pairs, decaying again to dark matter, or in this way. Now, dark matter, by definition, is dark. It means that it does not interact very strongly with us. So dark matter, once it's produced, would go through the detector without leaving any sign. It's not like a charged particle that would, get trapped in the field, in the magnet, or like a photon. If you try to shoot a photon across that wall, these detectors, they are like, meters of steel. So to go through them, you really must be very, very weakly interacting. Otherwise, everything gets stopped. With a laser, I cannot go across that wall, right? I will get stopped. But dark matter interacts very weakly because we don't see it. And therefore, it would really go across the steel walls of the detectors. And by going away, it would leave what we call a missing energy signal. We know how much energy we put into the system. If some of this energy goes away without us measuring it, it means that something must have escaped. And something that has escaped has the properties of being dark matter. So this is how the production of a WIMP, a weakly interacting massive particle, a dark matter candidate. This is a simulation, so it's a computer-generated event. This is how it would look like in one of the LHC experiments. You see, we produce jets on one side, these objects, these flows of particles. They correspond to the manifestation of a quark after it's been produced and evolves. And you see that there is nothing on this side, okay? The stiff objects, so the straight tracks, are those which carry most energy. And you see that on this side, there is nothing stiff. There is nothing carrying away energy on this side. So we're violating here the basic principle of action-reaction. If when I shoot with a gun, the bullet goes that way and I recoil back because we need to conserve momentum, as we say. Here, we have a bullet going that direction and there is nothing coming behind. So this would violate basic physical laws, but the point is that there is something recoiling here, we just don't see it. That would be the dark matter I'm referring to. Now, one of the problems is that there are other processes in the standard model that would look exactly the same, and that's why it's very hard to look for dark matter at the LHC. For example, I can produce a W boson. The W decays to an electron and a neutrino, and the neutrino also interacts very, very weakly, and we wouldn't see it. Or we could have the production of a quark with a Z, and the Z goes itself to neutrinos. So this is an example in which, in fact, there is a jet on this side and nothing on the opposite side. But this is interpreted as being the production of standard model objects. So there are backgrounds. Like in every experimental measurement, there is always some background, and one has to learn how to deal with them. And when the experiments go out and they count the number of events in which there is missing energy, and they distribute them as a function of how much missing energy there is, you see these points correspond to the counts, and it means that they do see a lot of events with missing energy. But when they account, they go and they look at what are the possible sources from the standard model. There is a pile-up you see here in different colors, it's different contributions. There is this Z goes to neutrinos, which I mentioned. There is the W goes to electron, which I mentioned. There are others that I didn't mention, but are still. And when you sum them up, it reproduces exactly the data. If there had been some source of missing energy beyond neutrinos, for example, dark matter, then we would not have seen this shape. We would have seen a shape like, for example, these green lines, this dashed green line. There would be an additional contribution coming from those other processes. So since we see no evidence that there is a difference, relative a discrepancy with the prediction of a standard model, we conclude that, unfortunately, for the time being, there is no trace of dark matter being produced at the LHC. It does not contradict the fact that dark matter is there, of course, and it does not preempt the LHC from discovering dark matter as it continues. In fact, the LHC is continuing for the next 20 years, doing many things, among which continuing looking for dark matter. But certainly the fact that it's not been discovered so far has led people, theorists, to start thinking along different lines. And there is a new ingredient that's coming into the game from very recent measurements, which is the possibility that while dark matter interacts very weakly with us, so it's dark for us, it might interact relatively strongly with itself. So dark matter could actually be a world of its own that we don't interact with except for gravity and some very, very weak interactions. Now, at the beginning, it was assumed that dark matter would not interact with itself. For example, by looking at collisions between clusters of galaxies, these are two clusters of galaxies that came together, they collided, of course, a long time ago, but we see the fragments. And by doing measurements similar to those I described at the very beginning of gravitational lensing, we can tell where is matter and where is dark matter. And what we find is that all of the matter kind of got trapped. You know, as you can imagine, there is a collision. So everything that interacts strongly stays there. And things that don't interact very strongly with themselves, they just fly through. And this is what seems to have happened to dark matter, because dark matter just went through and is shooting out of the collision region. So this led to limits on the amount of self-interaction of dark matter. On the other hand, looking at the way dark matter is distributed inside galaxies, does not match this picture that dark matter does not interact with itself, because instead of being very sharply peaked in the core at the origin of a galaxy, it's distributed much more smoothly. You see, this is self-interacting dark matter, while dark matter that does not collide with itself would have a more peaked structure. This is the density as a function of the radius from the center of the galaxy. And this self-interacting dark matter density profile is what is favored by data. There are very recent measurements now, again, of systems where clusters of galaxies collided. There is this one, I'm not sure, I don't know how much you can see of it, but there is light, which are galaxies, and there are these blue profiles and contours. They are the contours of density of dark matter. They tell us where the dark matter is. And as you see here, there is a mismatch between the position of the galaxy, the visible matter, and this blue contour that gives the density, the higher density of dark matter. And if one tries to interpret this separation, one finds that indeed this can only be accounted for if there is some self-interaction in dark matter. So this is an open issue. It's growing in interest, and on the theory side, people start thinking along the lines of dark matter as being really a secluded universe, not a universe in the sense of space and time, but in the sense of a world. It interacts with itself. There could be complexity, as we do have complexity in our world. There could be a dark matter sector standard model with many particles, with interactions in there. There could be a chemistry or at least a nuclear physics there, and we just wouldn't know it. We would only perceive the gravitational effects. You know, we could have beings flying around here. There could be a meeting, a conference in this room of dark matter people listening to the latest findings about dark matter in their universe, which is us, because they would see our presence, but they wouldn't feel it, and they could wonder what the hell is that 20% that's unaccounted for. For us, it's a factor of 5. For them, it's only 20%. Now, it will never get as far, because certainly these interactions would not be, they wouldn't have a chemistry, they wouldn't have a nuclear physics like the one we have with our normal matter. So it would most likely be completely idle, but it's a very interesting possibility. There is a possibility that the Higgs boson is a bridge between our visible matter, the standard model, and the dark matter world. There are theories that are being developed consistent with these scenarios. They have features that make them very appealing to address some other issues. And whether these theories give rise to observable phenomena is under discussion. So the exploration of dark matter continues. It's not been detected at the LHC. It's not been created at the LHC. It's not been detected by the other experiments that I mentioned, and that will be reviewed in Bertone's lecture. On the other hand, particle accelerators like the LHC offer the unique opportunity to directly produce dark matter. So even if dark matter were to be discovered directly through the satellite experiments and the underground experiments sensitive to direct and indirect reactions, even if that were the case, we would still need to produce dark matter directly in the laboratory if we really wanted to probe precisely what its nature is, what its interactions are with the matter we know, so that we could learn more, and in particular we could test, for example, this idea of dark matter having its own complex environment. So the search for dark matter remains one of the key tasks of the LHC, and we're looking forward to the next 20 years of LHC operations to learn more about its properties and hopefully its existence. Thank you.